Hello, ladies and gentlemen. We are group number 7, also known as the A team, and we worked with John Deere this past semester at their seeding facility in Moline, Illinois. And the objective of our project was to optimize material flow between forklift travel on in their plant. For our problem statement, there's non-value added activity with receiving and shipping operations, as well as inefficient material flow. And kind of lastly, we were trying to idealize the locations of shipping and receiving docks. Currently, part materials flow through the west dock, and they're transported via forklift to various cells within the facility. There are also materials that are received via the east dock, but those stay in cells close to those for weld parts, so we did not focus on those in our scope. Just a quick view of the current state. There was a lot of non-value added activity with the receiving and shipping operations, as well as there's inefficiencies of material flow. So currently, most part materials flow through the west dock and are transported via forklift to various cells throughout the facility. And an operator knows where to locate this material from move tickets. And we noticed that there's a lot of transportation, let's say from the west dock to cells more to the east side. So our goal was to figure out the best and most efficient way for forklift utilization.
All right, so here's the methodology tab. On the top left picture, you can see that this is the part routings. We have the methodology on the right-hand side, the right-hand picture. That's actually going to show where our maximum time is, the forklift method, and then the tugger method. And then on the bottom is the processing tab. And we made a process to demonstrate unloading and loading of the parts. And then this is Flow Planner. This is some diagrams that we have from Flow Planner. The Contigos are the purple maps, and then the totes are the blue. And on the top left is the fan diagram. And the fan diagram is just going straight from the west dock to the parts. And then the bottom right diagram is actually the aisle pass that they have to take. And here's a congestion diagram. As you can see, the red is indicating more flow, whereas the blue is indicating less flow. And here we show the distance, the time, the cost, the travel percent, and the average trip. Overall, for the current state, we have about 720,000 as the distance and about 80 hours.
One of the first steps to this project was validating that our model in Flow Planner was accurately representing the actual system. So in order to do a simulation, we needed to make sure that we were actually showing the number of or accounting for the number of workers that were currently in the facility. We ran our data in Flow Planner where we had the frequencies and locations of deliveries, and were able to calculate the number of workers necessary in order to make these deliveries. What we found out is that about 12 and a half workers were necessary to make these deliveries in our simulation, which accounts for the 13 workers that were used in the actual facility. Also, another assumption we made is that 1 day's worth of data could be used in our Flow Planner model. In order to validate this assumption, we checked several different days that had different volumes of deliveries, as each day is going to have different frequencies of deliveries. And what this chart shows us is that the change in distance and the change in time from the current state to a new layout is about the same for each of the days that we tested.
Okay, so here's option 1. As you can tell, with this fan diagram, it kind of shows where we kind of split up the different parts. We have the west dock just distributing those legacy parts. And then we have the central dock here, which is distributing the rest of the parts. And then the bottom right, you can see the aisle diagram flow. And then here's actually the congestion diagram. So this congestion diagram shows that we have the majority of the parts still being sent to the west side of the facility. And we have the distance, time, cost, travel, everything that we had in the current state, just to reference for them. And then here's option 2. This is how we split it up. We split it to the west dock, central dock, and then the east dock kind of the same thing here. And then here's the congestion diagram. We were able to find the distances, the time, the cost for all of these as well. And as you can see, there's some aisles that are being used a little bit more than what they currently would be at the current state. And then here's option 3. We have most of the parts still being continuously used through what they are doing with the current state, having the parts go in at the west stock. But we did use some of the east stock here. We were able to take the east stock, distribute some of the parts there. About 80% from the west and about 20% from the east. And here's the congestion diagram with these distances, times, costs, etc. And then here we just picked some points on the facility layout. We're able to pinpoint these points, and then we're able to find out the frequencies just to tell if these aisles were used more, and we could take this data and be able to talk to John Deere and show them that these aisles might need to be looked at for any changes to make sure that there's any safety precautions or anything that needed to be taken into account in order to make sure that the aisles are safe or needed to be changed.
In our current state, we calculated the cost of material flow in 3 ways using employees, forklifts leasing, and the gas usage for traveling and material flow. By reducing these, we were able to estimate the cost savings for each of our options that we talked about previously. Option 1 gave us savings of $280,000 a year. Option 2 gave us savings of $350,000 a year, and option 3 gave us savings of $152,000 a year. With a project of this size, a 10-year payback period was assumed for a large factory change like this one. So after 10 years, the net present value of each of these options listed here. Although the only one that had a positive value was the third option, having no initial investment, and the savings are the only calculations made. The payback period for these types of projects are going to be 10.7 years for the first option, 8.5 years for the second option, and no payback period with a theoretical $0 investment for the third option.
Ultimately, the goal of this project was to come up with the best locations for receiving and shipping in the facility that will reduce material flow. Our group explored several options that would make improvements over the current state. While some of these options would reduce the travel distance further, they may have additional costs that would make them infeasible for the current time period. One of the options we looked at had a high investment cost, but it reduced the travel distance by the largest amount, while another one of our options didn't have as big of a reduction in travel, but there was much less investment, and that option may be more feasible for the short-term payback.